All right. Let's get started. So I'm going to continue from last time. I said we were going to do time discretization bounds for DDPM. We spent 10 minutes talking through it. Again, I'll just talk through it once more, just to recollect. Okay. So there are the going back to DDPM. A DDPM dynamic is of this form. At time t minus 1, it's some scaled version of this latent state at time t minus the score. And this ideally, this is, what is this? This is some xt plus some conditional expectation of x0 given xt, some constants here and here. Okay, it's affine in the conditional expectation. And so this overall dynamic looks like xt minus 1 is some constant 1 xd plus constant 2 times conditional expectation of xt given xt minus 1 plus some noise, right? That's the way this dynamic looks like. And when we studied that, we sort of we argued that that is indeed a discretized version of the continuous time dynamic. And we saw that for the continuous time dynamic at time 0, you do indeed truly sample from the true ground truth distribution. So all that was established over the last several classes. So now we want to see what is that discretization error. We want to see what we can say for DDPM. We have done this for Langevin dynamics and Langevin Monte Carlo over the last couple of lectures. So today, let's just look at DDPM. And the method I'd like to sort of overview is this information theoretic proof for diffusion sampling. It's a recent paper by Galen Reeves and Henry Pfister. There are several. This is not the first proof for this. There are earlier proofs. The first proof for discretization was this paper by Chen Chui et al. This one. Then follow up the Holden Lee and colleagues, and then Benton and colleagues. So these are all sort of earlier proofs which are interesting, but I decided to sort of present this proof because it shows new machinery which would be of interest to us. Okay. So we are going to study the following dynamic. So zk, so we are not looking backwards in time. Everything is just moving forward in time here. The dynamical system is zk equal to zk minus 1 plus some delta k times some function of zk minus 1 plus some noise standard deviation times a Gaussian. This is the generic dynamic we are going to study. How is this related to what we have studied earlier? Well, if f was equal to conditional expectation of, let's call the ground truth x0 given zk minus 1, then you see this dynamic is essentially some form of the discretized DDPM dynamic. Okay, because the next state is affine in the current state and the conditional expectation plus some noise. By choosing the constants appropriately, you can match everything up. Yeah, right now, the way we are talking about it, we will define a general dynamic of this sort and just analyze that. That's all. It's a scalar. It's not like a delta k is delta sub k is not a delta function. It's just a scalar step size. That's all. Okay. And this is the delta k is used in two places. It's used as the step size for the drift, and it's used as square root of that is the same delta k is also used for the diffusion term in this generic dynamic. Yeah, f can absorb anything exactly. But we will look at a particular f. We will see what f pops out, which is the correct f. This analysis will for error. Okay. And this one is just Gaussian, zero mean, identity covariance. Okay. This is a generic dynamic. At this point, for a general f, it has nothing to do with DDPM or any such thing. It's just a dynamical system with some drift and some diffusion, some noise added. That's all. Okay. So now next we are going to define a companion process. The companion process is the following. Yk equals, so first we start with y0 equal to 0. Let's start with that initial condition. Okay. And then yk is yk minus 1 plus the same delta k step size times x0 plus root delta k times some Gaussian noise. Okay, this is just some independent Gaussian noise. We just call it W hat instead of W tilde. This is another dynamic. That's why we just put a hat on it. Note something important here. X0 is the ground, a sample from the ground truth. Every subsequent dynamic step depends on the same sample. You're not resampling anything here. You're choosing one X0 and keeping it fixed. Okay, and then this dynamic is being updated this way. So let us rewrite this. Let's unravel this dynamic. So X0 is from the ground truth distribution, mu star. Okay, and X0 is independent of all these noise. I'm just looking at this right now. We have forgotten the actual dynamic. We are just looking at this companion dynamic. Okay. Then, so here Y0 is 0. What's Y1? Well, Y0 is 0. So Y1 is delta 1 X0 plus root delta 1 W hat. Okay. So Y1 is delta 1 X0 plus root delta 1 W hat. What's Y2? Now you stick in Y1 into this. Here, you'll get Y2 is Y1 plus delta 2 X0 plus root delta 2 W hat, which means, but W1, we can just substitute for Y1, we can just substitute this in, which means delta 1 X0 and delta 2 X0 combine to give delta 1 plus delta 2 X0. And the noise combines in root of delta 1 W hat 0 plus root of delta 2 W hat. How did I get this 0? Give me a second. Something is wrong in what I've written here. The Y1, my apologies. Let me fix some typos. There should be W1, there should be W2, there should be W1 and W2. Am I correct now? Okay. So this is the dynamic, and so this is what you get. Now these are independent Gaussians, zero mean unit covariance. So that means this is just a scalar, which means that effectively this whole thing is a Gaussian with variance, this one square plus this one square times identity. Okay, so let us define the sum of deltas as Tk. So Tk is delta 1 plus delta 2 up to delta k. Then what's going on? X0 is being multiplied by Tk, and W hat is essentially a Tk variance Gaussian, the effective thing. Okay, meaning if let's call that Wk as Gaussian with zero mean variance. Okay, that's what this is. Good so far? In which case we can just write Yk dynamic in this form. Yk is nothing but Tk X0 plus Wk. Once you write it this way, let's just understand what this Yk thing is doing. Okay. So if we choose, I haven't told you right now, Tk deltas and all are very general. F is all very general. We haven't said anything. In any case, otherwise there's no F. There's just this delta sequence. Okay. So if we choose del Tk as scaling as 1 over k, okay, meaning we'll have some constants floating around, some dimensional dependent constant, epsilon and all that. But at a high level, let's say Tk goes down as 1 over k. I'm sorry, delta k goes down as 1 over k. Then Tk is 1 plus half plus 1/3 up to 1 over n, which is roughly log n. Okay. So which means in this dynamic, this thing is log n. This thing is root log n. Why am I saying this thing is root log n? This is a random variable whose mean is 0 and the variance is log n, and therefore its standard deviation is root log n. So at least for a hand wave purpose, anytime you see a Gaussian and you want to see what size it is, its size should be order standard deviation. Okay, that's the magnitude of that thing. Okay, so the point is that this is an order log n quantity, this is an order root log n quantity as time progresses, as k progresses. Okay, which means that this is roughly becoming, if I look at this and scale it by Tk, then this one should be roughly X0. Small perturbed version of X0, but essentially X0. Is the intuition making sense? So last time there was some confusion on that intuition, so I just wanted to talk through that once more. Where is the log coming in? So no, we are not. Wk is the sum, correct? So that means what is this? This is identical in distribution to some random variable, which is zero mean and covariance tk. I mean, not covariance, variance tk. And so that means if wk is an order, it has a variance tk, its standard deviation is order root k, root tk. Okay, and so that's why tk is log n. Oh, because I'm saying suppose delta k is 1 over k. I'm in this mental model. I'm just keeping, just to get some intuition. I'm assuming delta k is 1 over k. Okay, in which case then yk by tk is roughly x0. I can just ignore the noise. That's all I'm trying to say. Okay, for k large. Wk is order root log k. Yeah, exactly. It's small, exactly. Okay, so therefore, yk is, I'm just motivating where this why yk is defined this way. So yk can be thought of as sort of an approximate version of x0, effectively, for k large. Okay, and for larger and larger value of k, you'll get a better approximation. So you can think of yk as quote unquote a tracker for x0. Really, what we want is to show that this thing, under appropriate choice of deltas, and not this one, sorry, this one, under appropriate choice of delta and this function f, is going to sample from x0. That's what our higher level goal is. Okay. Instead, what we are going to show is zk tracks yk. And since yk for k large is roughly ground truth, will be done. I'm just telling you why this process, companion process, is being set up this way. Are you good so far about the motivation and these things?
X0 is an image or X0 is distribution?
X0 is a sample from the ground truth distribution. So if it's an image, X0 is that image. You want to generate. No, we're not doing posterior sampling or any such thing. We're just doing generative modeling. Okay, which means what the goal is, somebody gives you mu star and you want to generate an X0 from that mu star. Yes, these are all in KL. Okay, and so and therefore Z0 will be hopefully close to X0 in distribution. Not Z0, Zn. It's in forward time. Okay. Is that making sense now? The pipeline. Okay, good. All right. Some other things we need to remember that WKs are not independent, first of all. Okay, they're not independent Gaussians. Why? Because WKs are defined in this additive manner, right? It's each time WK plus 1 takes WK and then adds one more term to it of root delta K plus 1, W hat K plus 1. These W hats are independent Gaussians, but not these Ws itself. Okay, so you can check. This is a calculation you should be able to check from your random processes, that if you have this kind of a process, then the covariance of WK comma WM is the min of TK comma TM times identity. Okay? You can just check this calculation. And then of course, in particular, when K equal to M, then you just get TK or TM respectively, which is what you want. But for anything else, you get this. Okay. Further, now we have talked about this intuition already. Yk by Tk, we saw is exactly equal to, this is sample path equal to x0 plus Wk by Tk. So what is Wk by Tk? Well, Wk has variance Tk, Wk has variance Tk. So when I scale this by Tk, then A square. So 1 by Tk square. So the variance of Wk by Tk should be 1 by Tk square times the variance of Wk, which means 1 over Tk is the variance. So this thing has tiny variance. Okay, this one's variance is this object is a Gaussian with 0 mean and identity by Tk. So that diagonal with every diagonal term being 1 by Tk. That's all I mean. This Tk is a scalar. Okay. So which means that yk by tk is nothing but the ground truth distribution convolved with a Gaussian with some small variance, which means a slightly smooth version of the ground truth distribution. Okay, and this Gaussian notice is going to become more and more spiky because the variance is going down as k increases. Okay. So it's roughly for k large, this one and this one will be close. Okay, fine. So this is the main theorem, and we'll prove it through a series of lemmas. Somebody had a question? Yes.
If WK over TK is a unit Gaussian, why is this convolution correct then?
WK by TK is not a unit Gaussian. It's a Gaussian. So yes. So the reason is the following. Okay, let's do scalars. It's just easy to just say. Okay, suppose WK is a Gaussian with mean 0 and variance TK. Remember, in the scalar version times identity. I'm just looking component by component. Okay, and because it's 1 by TK, variance of A times X is A square times variance of X. And so that's why that 1 by TK square comes in. Okay. Yeah. So we're good so far? All right. So the main theorem is the following. Look at the KL divergence between the joint distribution of the Y sequence and the Z sequence. Okay. So then let's assume that the ground truth distribution has finite second moments. And furthermore, the expected value of the drift function squared is less than infinity. In this case, it means the average square in expectation, the score function is finite, which is a very reasonable assumption. Okay. Then delta n, the KL divergence, is bounded by the following two terms. First, delta max, which is the largest of the step sizes, times the trace of the covariance of x0. So this is the data. So let's see how this object is. Covariance of x0, if it will be order d. Presumably, if x is full rank, then it's order d. Okay, and I mean the trace of the covariance of that will be order d, okay, because each eigenvalue is on order 1 quantity. And so the first term is sort of delta max times d type of term, where d is the ambient dimension. The second term is the step size times the difference in expectation between the function you're using and the conditional expectation. Okay. So basically, this is already telling you that fk should be conditional expectation if you want to get the second term down to 0. Okay, that's what this is saying. Okay, so in particular, therefore, if you use the step size, the function you're using is simply the conditional expectation of yk, conditional expectation of what the ground truth is, given your current noisy latent. Then this is essentially what we are doing is from 2Ds. This is the score. Okay, that's essentially what we are doing. Okay, so then this selection of fk corresponds to a DDPM algorithm. And so now, instead of sampling from the ground truth mu star, let us sort of change the problem a little bit and say that I want to sample not from a ground truth mu star, but a slightly smooth version of it. Okay, and what you mean by slightly smooth is this. Let's take a Gaussian with 0 mean and with epsilon. Epsilon is yet another, it has nothing to do with delta. It is just some other parameter. Choose epsilon small. And the smaller you have epsilon, the closer that convolution of mu star and the Gaussian is to mu star itself. Okay. Then if you choose a step size as epsilon by n, then this combination, this a plus b implies that the what's a plus b? A is that this selection, b is this selection of step sizes. You can check that this implies that your KL divergence will have 1 by n epsilon times some trace of the covariance. Okay, and furthermore, this I'm not going to discuss in the class today, but from the paper. Furthermore, if fk is such that it returns a random value instead of the deterministic value, whose moments match not this conditional expectation, but the rth moment of the conditional expectation, then you can get faster rates of convergence as well. But all this you can look at in the paper. What I want to focus on is just the main line. Yeah.
Sorry,
the epsilon by 20. Wait, also, why is the n coming in? Isn't it delta max?
So all this, there's some more algebra that's coming. Delta max will be 1, okay? Will be epsilon. Delta max will be epsilon. How are we getting that 1 by epsilon? You need to do some algebra to get there. I didn't write that out. This is not just plug. You play around and some balance some terms, that thing happens. Okay. Yeah.
What if we do? Oh wait, it's 1/. Okay, sorry, because you're saying as n goes to infinity, it goes to.
Yeah, exactly. You have exactly fix any epsilon as n goes to infinity. That's the kind of statement you want.
But as epsilon goes to 0, won't you expect it to be better, not worse? Because your
No.
discretization errors are.
No, as epsilon is how precise you want the ground. Epsilon is not discretized. This is epsilon. As epsilon goes to 0, it gets harder and harder because you want the true ground truth.
This from the
So it should have an inverse dependent on epsilon.
Yeah.
Yes.
the first line you said from A, you have delta max trace covariance.
A?
Or sorry, yeah, this line here.
Yes.
I don't understand how you get rid of, like, if FK is the expectation, then the second term is 0.
So delta max is, so second term goes away. Delta max is 1 by n epsilon.
But delta max is epsilon by n. Sorry, delta max is just epsilon.
Delta max.
Yeah, it's delta is 1.
Oh, no, delta max is, yeah, epsilon by n.
Delta max is epsilon by n. Where's the 1 over delta coming in?
No, it's just by n for all the false.
Have I written something wrong here? Give me a second. It should have an inverse dependence. Why is that? Choose delta k really small. So delta max is just
It's not
epsilon by
particular
n.
trace of covariance of x.
Give me a second. First of all, delta max here, this step size is just, note, it's just fixed. Delta max is also epsilon by n. Okay, first point. I'm trying to see where 1 by epsilon square comes in somewhere.
Trace, it's not going to be of x0, but it's x0 convolved.
Yeah, exactly. And
Yeah.
then something is going, the 1 by epsilon square should come out somewhere there, I think.
X0 in the gas independent, you should get a plus epsilon.
But that will E.
Let me punt that discussion offline. Okay. Good point. Let me get back on that. I don't want to sort of do this real time. So I need to check whether these scalings are correct. That's the only thing I need to check. But this statement is correct. And if you choose the parameters correctly, you can get a ground truth. You can get a good approximation to the ground truth distribution. That's the point I wanted to make. I'll go back and see whether I have written something wrong here. But okay, the key construction here was there's this yk which has the ground truth all the time buried in it. Okay. Whereas z is a dynamic which we are tracking. So first, let's look at this yk process and show something very surprising, at least to me, something very surprising about this. So what is yk again? It is nothing but tkx0 plus wk, where wk is a Gaussian with 0 mean and variance tk with a covariance which is diagonal. The surprising result is that yk is a discrete time Markov process. Okay. Writing it this way, it doesn't look Markovian at all. It's the same x0 again and again which is appearing. Okay. It's just some different variance of noise added each time. But it's very surprising that yk is the Markov process. And furthermore, x0 is conditionally independent of y1 through yk minus 1 given yk. Okay. If it's a Markov process, then that's true. But this B is an implication of A. But why is this a Markov process? And why is this true? Okay. Let's prove this. I really like this proof. This is very slick. I think these are the heart of the Reeves and Pfister's proof is this and the next lemma. Okay. So consider the difference sequence. Vk is yk minus 1. So again, always remember what yk is. It's just tk x0 plus wk. Okay. So vk is yk minus 1. So that difference, what is that? Well, by definition, this difference is nothing but delta k x0 plus root delta k w hat k, where this is just a zero mean Gaussian. If you have forgotten why this is by definition, you go back to the construction of yk. We started with yk as this dynamical system, which means yk minus 1 is just this. Okay. This implies this other way of writing it, but you can always, this is where it started from. So let's look at this different sequence of vk's, v1 through vn, and let's look at the conditional distribution of v1 through vn given x0. Okay. So if I tell you x0, then each of these vk's is just a Gaussian with a shifted mean because x0 is known. Okay, so condition on x0, this is just zero mean Gaussian. This is scaled, and this is a known constant because I have condition on x0. Good so far? And therefore, the joint distribution of v1 through vn given x0 is just nothing but a product for, and all these w hats are all independent Gaussians. So that means the joint distribution is just a bunch of, it's just a product form of Gaussians, okay? Which means it's 1 by root 2 pi, the variance delta I to the d by 2, because covariance is identity. I don't, all this inverse and all that, none of that I need to keep track of, times in the exponent, it is 1 by 2 delta I, vi, that's the variable, and the mean is just delta I x0, okay? Just a shifted mean. That's all this is. So now let's simplify that. So you can complete this square out, you can expand this out, and then what you get is the following. So you'll get all these norm vi squares, you'll get norm x square, and you'll get inner product of vi x0, right? When you expand that in the exponent, the norm of vi minus delta x0, you'll get these three types of terms. You pull them all together, you can write it in this following form. Each one of those vi squares will itself, each is scaled by 1 by 2 delta I. You'll get the exponent 1 by root delta I vi square. You can take this part of the constant and put it with that. And this just becomes a zero mean Gaussian with the variance delta I times an identity. They're all product form, so you get this. The remaining parts, you'll have an inner product of summation vi, because when I take the product of these exponents, all those inner products add up together in the exponent. Okay, so you get an inner product of summation vi x0 minus, if you combine all these delta i's, 1 by delta I, the squares and all this stuff, you'll get a tk by 2 norm x0 square. Okay, this is algebra. You have a question, Jacob?
Just because TK is summation delta I.
Exactly, tk is summation delta I. Exactly, it cancels one of them. Okay, now y0 was equal to 0. So this summation vi is just yk because it telescopes. Vk is yk minus 1. Vk minus 1 is yk minus 1 minus yk minus 2. So the alternate terms cancel. It'll just give me summation vk is nothing but yn minus y0. But y0 is just 0. So it just gets the last term. Good so far? So this summation vi is just yk. So where are we at this point? We have basically shown that the joint distribution of this difference sequence, condition on x0, can be written as something that depends only on vi, and the other part which depends only on the dependence, the relation between x0 and vi's is only through the summation of vi's, which is yk. So
You're using K.
yn, I equals 1 through k, summation of vi I equals 1 to k. Oh, I've switched k and n. Okay, good. Let's fix that. This should be n, right? This should be n. This should be n. This should be n. Is that correct? Then I think I've got it right. Is that correct now?
Yeah, you just.
Okay. Okay, thank you. I think now it's correct. Okay. So now let's step aside and go back to some classical statistics, the Neyman-Fisher factorization theorem. Okay. What does it say? It says that if I given a collection of random variables v1 through vn, I'll just put a v bar for a vector. So let f v1 through v1 semicolon x0 be a density function with parameter x0. Okay. So for example, if you're in a Bayesian setting, you would look at you could look at the joint distribution of v1 through vn condition on x0 or whatever. Okay. But now t of some function t is a sufficient statistic for x0 if for any prior distribution over this x0, the conditional distribution of x0 given this function of v1 to vn is the same as the conditional distribution of x0, not just given this function, but also given the individual components. Then t is said to be a sufficient statistic. Or equivalently, from an information theory point of view, the mutual information between x0 and this function of function t, this is a new random variable, t of v1 through vn, will be the same as the mutual information between x0 and actually if I know all these v1 through vn, right? In words, knowing t versus knowing actually the v1 through vn are both equivalent as far as you want to predict x0. That's what it's basically saying. Okay. So, and this is the following Neyman-Pearson factorization theorem. A statistic t of v is sufficient if and only if there are functions h and g such that the f of v with parameterization x0 can be factorized in the following way. Something which just depends on this v vector and something else that depends on g and the sufficient statistic. You need to have this factorization. So I can see some people looking confused. So it's basically saying this distribution has some coefficient that depends on v, but that part that relates v and x is depends only through t of v. Okay, that's what this is saying. Does it make sense? Okay, so let's go back here. That's exactly what this is. Here, that part that relates v and x is only through y, which is the summation of vi. Okay, so what is this saying? So which means yk, which is summation vi, is a sufficient statistics of x0. What about it? This is the function. This whole thing is a function. I'm saying this function depends only on y. In this function, there is only y and x0.
Yeah.
Okay, and therefore, this is a sufficient. H is that whole thing. E to the blah 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 is the whole thing. I'm sorry, g. This g function is this whole thing. And therefore, yk is a sufficient statistic for x0, which means that x0 is conditionally independent of v1 through vk given yk. Okay, which means x0. But now unravel what these things are. Assume now we know y0 equal to 0, which means x0 is conditionally independent of y1 through yk minus 1 given yk. It's a very slick proof of Markovianness. Okay. I really like this proof. Okay. Agree? Just to know this is very surprising to me because it looks like that just adding that little bit of noise each time essentially is giving you a Markov chain. Okay. It's very cute. Okay, so this is step one. Step two, this above fact immediately leads to so what we have shown is Markovianness because we have shown conditional independence. Okay, we haven't shown Markovianness. We have shown that at this point we have shown that x0 is conditionally independent of y1 through yk minus 1 given yk. This almost, it looks like intuitively this should imply Markovianness because x0 is the terminal state of the y process. It's going towards that. Okay, you're basically saying that you come up to k minus 1, you look at time k, none of the future matters from the past, and therefore it looks like it should be Markov. Okay, you can make this formal, exactly what I said. Okay, but we'll not do that. I want to prove explicitly from here Markovianness using a second, they have a second proof which is also really beautiful because it shows you how another way to sort of prove Markovianness. Okay. Again, recall what Y is. Y was essentially, here, this is a dynamic. You can write in iterative form, which is yk equal to yk minus 1 plus some delta k minus 1 x0 plus root delta k minus 1 w hat. That's another way to write it. So now instead, let's look at this new process bk. Okay, it looks like it's just pulled out of a hat, but we'll see why this is an interesting process to study. Okay, it is some weighted difference of yk and yk plus 1. The weighting is root of tk plus 1 by tk for this one and root of tk by tk plus 1 for this one. Just written, we have just defined this bk. But remember that yk is nothing but tk x0 plus wk. So let's just stick that in. So yk is, this one is tk x0. I'll ignore the wk part of it. I'll look at it separately. This one is tk plus 1 x0. There's a w part of it, which I'll look at it in a second. So this tk cancels with this root tk to make the numerator root of tk plus 1 tk. And for this side, this tk plus 1 cancels with this root tk plus 1, giving the numerator as root of tk plus 1. So this and this cancels. The x0 part completely cancels out because the coefficient of the x0 part on both sides is root of tk times root of tk plus 1. It leaves the other one that doesn't have the scaling. So you will get a root of tk plus 1 by tk wk. For this, you will get root of tk by tk plus 1 of wk plus 1. That's what bk is. Right. Now, the second claim is bk is conditionally is just independent of w of all future wk plus 1, wk plus 2 up to wn. Let's see why. Okay. Now you see bk is a function of wk and wk plus 1. And the claim is this is independent of every one of these things in the future. Why? The covariance of wk and wm, we saw that it's just a min of tk comma tm of r. Okay, that's what the covariance was. So let's say m is greater than k. Then covariance of bk and wm, which is nothing but, now I have a wk. What's the covariance of wk and wm? It's just tk itself because the min. And for the other one, for the tk plus 1, we'll just get the tk plus 1. And this cancels. That's all. Just substitute and check. Okay. So the covariance is 0. It's Gaussian. So W is just some linear transformation of Gaussians. So it's also Gaussian. For checking for independence for Gaussian sequences, all you need to check is covariances are 0. You don't need to do anything else. Right? So where are we right now? We have this BK sequence is independent of everything in the future. So this is what we had, right? BK is this times yk minus the inverse flip of that times yk plus 1. So let's rewrite that. I want to write it as a dynamic of yk now. So which means yk is, if you just do the algebra, tk by tk plus 1 yk plus 1 plus something times bk, where bk is just some Gaussian. And furthermore, bk is independent of all the future w's, which means, so look at this dynamic. Look at, this is a dynamic going backwards in time. Okay, so look at this sequence, reverse process sequence, yn minus 1 up to yn. Yeah, it's a process going backwards in time. It's Markovian because yk is a function of yk plus 1 plus some noise which is independent of everything else, of all the future noises. So looking backwards in time, this is a Markov process going this way in time, backwards in time. Okay, and this is this very, very cool fact that a Markov process is Markov if and only if its reverse process is Markov. Okay, this is a different way of proving things. I want to prove something is Markov, okay, and the dynamic is something crazy, But the reverse process dynamic is much nicer to analyze. So this is the reverse process. We have seen that the reverse process is Markov, and therefore the forward process has to be Markov too. Okay, so this lemma is, I think, cool for multiple reasons. One, in terms of sort of a statement, it shows something which wasn't obvious as Markov is actually Markov. And two, in terms of machinery, it's showing us two different ways to do show Markovianness. I mean, both which is not normally done. One is, I don't know how to analyze the forward process. Just write the reverse process and check whether that's Markov. Okay. Note that a caveat: the reverse process could be time inhomogeneous Markov, whereas the forward, it doesn't say anything about homogeneous or time inhomogeneous. One way could be time homogeneous, the other way could be time inhomogeneous or whatever. But if one way is Markov, the other side has to be Markov. That's a very, very cool statement, which is not obvious. Okay. That's statement number one. The statement number two is using Neyman-Fisher type factorization. If you got some process, you want to check Markovianness, you just check whether that state is good enough to predict whatever you want, the end state. Okay. And then you're done. That factorization allowed that. Okay. So that's why I spent a lot of time on this lemma, but it's because it's showing us sort of two very beautiful ideas. Okay. Any questions on this before I move forward? Okay. So what we have now is that this Y process is also a Markov process. So now the second lemma, which is going to now allow us to track the error between the X and the Y, between the Z process and the Y process. Again, recall, we started with the DDPM type dynamic with the Z process, which had no X0 buried in it. We brought in a Y process, now which we have shown is a Markov process. Okay, it's a Markov chain actually, discrete, because discrete time continuous state space. So it's a discrete time Markov process. Okay, and now we want to see how the KL divergence goes. And it says that the KL divergence between the Z process and the Y process is equal to the following. Okay, it's equal to, look at the MMSE error at each time. Okay, this one is trying to predict the ground truth X0 given your current latent state. This is a true latent state. This is your therefore, this is the mean square, this is a prediction error essentially. Okay, multiplied by the step size. Okay, then there's one more term, which is the mutual information between X0 and Yn, which should be hopefully small, because Yn is designed such that Yn should be close to X0. Remember, that's how the Yn dynamic was developed. So this should be something small. And the third depends on what is your drift function and the conditional expectation. If you indeed use DDPM, this is exactly equal to 0. But this also tells you other things. If you have a noisy version, what happens? If I use some other type of score, how is the error accumulated? All sorts of things come out of this thing, right? It's just a really clean expression. Okay, and so what is the mutual information? It's nothing but the KL divergence of the joint with respect to the KL divergence. On the other side is this product of the marginals. That's all. It's mutual information. Okay, so then let's do the proof of this. So Yk is a Markov process. Let's call Pk as its transition kernel. And sorry, what did I do? Okay, and Zk is a Markov process with transition kernel Qk. Just notation. So now let's do chain rule. For Markov processes, I can just do divergence decomposition for KL divergence. So the KL divergence of the joint of Y and the joint of Z can be written as the following. It's always the distribution with respect to the Y's, right? KL is always expectation with respect to the first one. So that's why I put in Y here. And it's nothing but the sum of the log of the ratio of the conditionals. And this just is from KL divergence decomposition for Markov chains. So what we need to track is just log Pk of Yk given Yk minus 1 with respect to Qk given Qk of Yk given Yk minus 1. This is for the Y process. This is for the Z process. So let's develop the expressions for numerator and denominator. Zk, the dynamic is it's drift plus some noise. So conditioned, so what does it mean? If I tell you Zk minus 1, that's my little Yk, then distance distribution given this is just Gaussian, because this is Gaussian, with an appropriate variance, and this as the mean, because I've given you this value. Okay, so that means Qk is just a Gaussian with the variable being yk and centered at yk minus 1 minus delta k fk of yk minus 1. You can just, that's it. And therefore, I can look at the log of this. Then what am I going to get? I'll get the 1 by root 2 pi. There's a constant in front that's going to give d by 2 log 1 by 2 pi delta k, and I'll get the quadratic. Yk minus 1 minus delta k fk, fk whole square divided by 2 delta k. Meaning the log of the density, the negative log of the density, you can combine, you can just do some algebra on this. You can take this. You can also, where is this coming from? So you can do let's take this to that side, subtract d by 2 from both sides. Okay. If I subtract d by 2 by both sides, this d by 2 can pop in inside as 2 pi e. The reason we want to get it in this shape is sort of differential entropy. We want to push it towards the sort of an entropy-like statement. So you will make it a 2 pi e and you'll get a minus d by 2. So let's just keep this expression in mind. Now let's look at, so this was the analysis of the denominator here, qk. For the numerator, which is the analysis of y's, well, yk is yk minus 1 plus the ground truth all the time plus some Gaussian. Okay, so we have this expression. This is from the zk. We have yk minus 1 here, for which we can substitute this in. I'm just doing algebra at this point. Okay, and now you get that the expected log of the denominator term has the following form. It's just some expectation of delta k x0, w hat, fk. All this is there. So I'll just expand this whole thing. Just bear with me. I'm sort of going through the algebra, but something neat is going to pop out in a second. It's this one square, so I can combine terms. This one and this one is combined to get something square, plus this thing, a Gaussian square, plus the inner product between this term and this term. Okay. This term square, we keep it. This is a Gaussian square. We know the Gaussian square is just d, the variance of it. The expected value of the norm of a Gaussian square is just dimension. It's a d-dimensional thing. The constant in front, you can just track that the root delta k square will become a delta k and all that stuff. And the cross term is 0 because w hat k is independent of x0 and yk minus 1. So this is 0. So finally, what we are going to get is this simplifies to just x0 minus fk of yk minus 1, which can be written as the following. I can add and subtract here the conditional expectation. So I'll get x0 minus conditional expectation square. I will get the second thing is the error because I've added and subtracted. But at this point, you're going to say, hey, where is the third term? When I add and subtract things, I will get a cross term. Why did the cross term go to 0 here?
It is orthogonal to y.
Exactly. There's a principle of orthogonality in estimation. Because if I was going to estimate x0 and ask you, what is the best, in the mean square sense, what's the best estimator of x0 given yk minus 1? It is nothing but the expected value of x0 given yk minus 1. This is the best, this is MMSE estimate. And therefore, we know the following. Is orthogonal to any other function of yk minus 1, which is trying to estimate x0. Okay, and so That's all. Principal orthogonality says the second inner product is 0 because you're dealing with the MMSE estimate. So you just have these two terms. Okay. So we went through a bunch of things. So let's just recap where we are at this point. So at this point, we have the denominator sorted out. It's just the expected log of the QK, which is the one-step density, okay, of yk given yk minus 1, shifted by some constant, can be written as the sum of two terms. One which is x0, the conditional expectation difference. The other which is the function and the expectation. This is the best estimate. This is if you're using the wrong drift, that's going to give you some cost. Good. Now we need some information theory. So so I'm just going to define things. We have used these kinds of things before. I'm just stating this. Conditional differential entropy is nothing but the expected little h of x given z is nothing but the expected value of the log of the density, conditional density. Okay? So remember that given x0 and yk minus 1, given the two endpoints, then yk is conditionally Gaussian. Okay? Why is that? This is just by construction. Given x0 and yk minus 1, yk is just conditional Gaussian. This is the Gaussian, it's just shifted by this mean. Therefore, the differential entropy of yk given yk minus 1 and x0 is just a Gaussian, which is log 2 pi epsilon variance times dimension. This is the differential entropy of a Gaussian. Therefore, the expected log of the pk plus this constant can be now written in terms of these differential entropies. It's nothing but this is by definition the negative of the differential entropy of yk given yk minus 1. And this is just, we see that. We just derived that. Okay. And now you can use chain rule. What is the definition of conditional mutual information? Is the difference between the entropy and the conditional entropy. In this case, the differential versions of the same. So this is where you get mutual information from. That this part can be written as a mutual information between x0 and yk given yk minus 1. Okay. You can further, now you can play with this differently. You can take this mutual information and decompose it using differential entropies differently. Instead of looking at the differential entropy of yk given yk minus 1 and x0, you can turn things around and ask in terms of x0. You can write this as differential entropy of x0 given yk minus 1 minus differential entropy of x0 given yk minus 1 yk. But we know that yk is a Markov chain. So if I condition on yk minus 1 and yk, this goes away. And therefore, you get it as this difference just with some algebra. I can see people are flagging. You can look at it offline if you want. Will finally give you that this can be written as the difference between the following. Look at the mutual information of x0 and yk minus the mutual information of x0 and yk minus 1. Okay. This is a beautiful expression. It's saying how much information, how much is the change in sort of information as you go from one step to the next step toward with respect to the ground truth. Okay. X0 is the ground truth. Yk is some noisy latent, which is as you go k up higher and higher k, you're getting closer and closer to xk. This is telling you sort of information gain as things are moving forward. Okay. So this is really a nice expression. So if you put all these expressions together, then you're basically going to get telescoping and finally get this expression. Okay. So this is what we started with. We have effectively derived it. You saw these various pieces come in. You saw where this came from. You saw where this came from. And this thing comes from telescoping all the expressions we talked about. Okay. Again, I would like to read through the lemma. I know I went through it rather quickly, but just read. It's all carefully written out, so you can check it once more. Okay. So what? Okay. So far, in terms of ideas, the first idea was to look at the surrogate process Y, which is a Markov chain, and relate this dynamic which we cared about to the surrogate process. And this allowed us to essentially decompose the error in this form. The third is the following. This is a very, very cool relation called the IMMSC relationship. Okay. So this is the equivalent of what we did with Wasserstein coupling or Girsanov transformation in spirit. What did Wasserstein or Girsanov allowed us to track errors? I look at two processes, they're slightly deviating from each other. How much error is there? Okay, right? That's basically what any of that machinery allowed us. This is giving us a different way to track errors. It's basically saying the following. Suppose I have a random variable from some distribution. Okay. I take that random variable, increase the signal strength. Think of B as some signal strength. I'll increase the signal strength by B. Okay. But add noise. Or equivalently, if I rescale this, because I can this constant, I can write this as divided by root B. Okay. I'm taking a random variable and adding some amount of noise to it, and taking the same random variable, adding a different amount of noise to it. How much information am I losing because of that? This is the mutual information between the random variable and some noisy version of it. This is a mutual information between the random variable and a different noisy version of it. So I'm looking at it, I'm looking at how much information. So this difference is how much information is sort of lost or gained, depending on how A and B are chosen, as I change the noise level. Okay, it's a very fundamental question. And the answer is this is exactly equal to the following. It's equal to the integral from this noise level to this noise level, or this signal level to this signal level. It's written in terms of signals of the MMSE estimation error of what? Okay, let's look at what this MFS is. Okay, I want to estimate x0, but what I have access to is a noisy version of x0, okay, which is root s x0 plus noise. So if s is infinity, then this is equal to x0 itself, because I know x0 exactly. So the conditional, when s is infinity, then the signal is much stronger than the noise. So that means I know x0 essentially. Okay, and therefore I can predict x0. So at s equal to infinity, this quantity is just 0. Okay, so m of infinity is 0. And as s equal to 0, I have no signal. Basically, I have independent noise, so I can't predict anything. This is nothing but the variance of what this signal is. Okay, because I have no, I mean, I'll just guess the mean. If I know nothing about it, I'm just going to guess the mean. And so m of 0 is nothing but the covariance in this case. Okay, or trace of the covariance. Okay.
And is that the derivative of this?
Yeah, I'll come. I'm going to do the derivative version, but first let's look at the integral version. Okay. So what this is saying is, look at how my estimation error tracks from A to B. That integral of the estimation error is equal to the difference in informations. Okay. This is called the IMMSC relation. So let's go back to something I mentioned this some time back, and now you'll see this. There are three fundamental relations which actually tie everything together. The first is Tweedy. It says the MMSC estimate is affine in this score. Okay, this is the grad log. We have understood this. We have seen it multiple times. The second, so now you can look at the Fisher information. The Fisher information, the expected value of the square. Okay. The second relation is saying that the MMSE error is affine in the Fisher information. We derived this a few classes back. The third relation is this one we looked at now, which is saying that the derivative of the mutual information is equal to the MMSE error, which is the differential form of what you're saying. And so now we have seen that this MMSE error is affine in the Fisher. So it's saying that the mutual information, derivative of the mutual information with respect to quote unquote signal is essentially Fisher, some scaled version of Fisher. But this mutual information is also KL divergence. So it's telling you how derivative of KL divergence in appropriate sense is the Fisher information, which actually which has been used again in many other proofs, because you can start for many recent proofs use the following. They bound something called action. How is some error to understand how KL divergence is changing over a path? You need to track some Fisher along the path. Okay, so these three relations are really the basic three relations, and you can start putting these together to get various things. Okay.
What lecture is this?
This was lecture 9. I did a class 9A. I did it sometime in the past. At that point, it wasn't clear why this was important. I just sort of said it's cool. Now you can see where it's coming back. Okay, you can go back in the past videos. You can look at this one again. Okay, so at that point we derived this. This is called Brown's identity. It goes back to 70s, and this thing is called the IMMSC, which was the Dongling Guo and colleagues, including Sergio Verdu. This is a famous paper in information theory about 2007-8. But if you look at the KL version, I think some other versions are no. Yeah. So you put these. This is useful for various information theoretic things, but if I'm just connecting it back to the kinds of things we are doing, you can think of it as is a relation between KL and Fisher, if you want to see it that way, by putting the other things together with this. But coming back to what we want to do. So what is this saying? This IMMSC is saying that if I want to see how mutual information at different noise levels, how much information is lost, it is nothing but the integral of the error between these 2 points. And this MMSC is decaying downwards. It's decreasing, right? Because at one point, it is at one end, this error is 0 at s equal to infinity. At s equal to 0 is a trace of the covariance. Okay, and it's monotone. That's something else you can check actually. So what this gives us is the following. It essentially, intuitively, we were even though this proof has no continuous dynamics of some underlying process, we are doing discrete stuff. And now you can use this to see what is the loss in information essentially of this discretization steps. Okay, and we'll see how that comes out in the proof. From lemma 2, we had the following. We had that the KL divergence had 3 terms in it. One is the difference between FK and if you are not using the score or the conditional expectation but you're using something else, then there's an error. That's inevitable. There's an MMSC error. This is what we want to handle now. Okay, and this one, which we sort of argued should be a small thing anyway. Okay. What we will show is that this whole summation is bounded by delta max times the trace of the covariance. Okay, so something to realize about mutual information. So if I look at mutual information between x0 and yk, what is yk? It's some tk x0 plus wk. That's what yk was. If I take in terms of information, if I take this and scale this by some constant, it doesn't matter, right? So I can write this effectively instead of, I can write this wk as root of tk times some Gaussian, and then divide everything by root tk to basically say this thing is exactly the same as root of tk x0 plus standard Gaussian, instead of doing any non-standard, right? I can, because from information point of view, yeah, x has the same information as 3 times x. Okay. All right. So Now I want to track the difference in mutual information between x0, the terminal yk, and x0 and yk minus 1. Okay. And this, from the IMMSE relation, is nothing but the integral of the MMSE error between those time steps. Okay. This difference in this is monotone decreasing. So I have upper and trivial upper and lower bounds. The trivial upper and lower bounds is one end and the other end, with this gap being delta tk minus 1 is just delta k. Okay. So the difference in mutual information is just bounded by these two quantities. Okay. So this is allowing us to now let's put things. What is m of tk? It is nothing but the MMSE error, which is the conditional expectation of x0 given x0 given yk. Therefore, now this difference, which is what we care about, that was in a bound, can be rewritten in terms of m's. Now we can telescope it. M k delta k mk. Okay. Let me see what I yeah. So I can rewrite. So I'll just leave this. So look at this. This is where the so let's draw the parentheses. This is what this was. So inside this, we can, at each time step, I can just add this. Why is it okay? Because when you sum all these things, alternate terms will cancel, leaving nothing but the first and the last term. Okay. So this is clear now at this point. And so now from the IMMSE, we have got this bound. We have gotten this. So we use this difference in mutual information to write this as a telescoping M sequence. Okay. We can bound this further by pulling this delta k to a delta max. Then these again telescope back to just give me trivial covariance. That's all it is. Okay. So I know I went through a bit of algebra here, but I wanted to focus on the key idea, which is the difference in mutual information. You want to connect it to the difference in mutual information between two endpoints. That's nothing but can be bounded by the time interval times, whatever the MMSE error is at either end. You get upper or lower bounds. And that can be used to telescope along the path to put everything back together. Okay. That's essentially what the point is. Okay. So this is the proof. There are many other interesting results here, which is how do you optimize step sizes? So there's a huge research line. People are talking about what's the right step size to use and things like that for good rate of convergence. These bounds are very interesting, in my opinion, for doing these kinds of things. Also, improved rates via moment matching. There are some sort of algorithmic insights in this paper. So I would strongly suggest you read this paper because it's a really nice paper, in my opinion. I'm not covering all of it. I just covered sort of some of the key aspects of it. But so over the course of the last few lectures, we have seen three different methods to understand discretization. One is using Wasserstein coupling, the second using Girsanov, and the third using this MMSE. And we did it for two different algorithms. Okay. This brings me to the end of this whole arc of standard sampling. So we started with the Markov process. We did we did the continuous time dynamic to sample. Then we went through VAE GANs and came up with the DDPM with two different ways to think about this, and finally came up with the discretization error. So this story is now complete. Now, next week, I'm going to rectified flow, and then posterior sampling, and then discrete diffusions. That's the arc. That's where we are going to switch modes at this point. Okay. Again, they're all closely connected to all this stuff, but this story has ended with this particular thing. Okay. Thank you.